And I just want to welcome everyone to today's CDY session. And we are continuing on our series of multi-messengers, cosmic rays and gamma rays. And today it's our pleasure to introduce Ruoyu from the School of Astronomy and Space Sciences at Nanjing University. The title of today's talk is Pulsar Gamma Ray Halos. So Ruoyu is currently at the School of Astronomy and Space Sciences, as I mentioned, at Nanjing University. And he is an expert on particle acceleration, on cosmic rays, energetic particle transport. And his research interests are wide and vast and include high energy and ultra high energy cosmic ray sources, neutrinos, particle acceleration mechanisms, candidate sources of these particles, such as pulsar wind nebulae, gamma ray bursts, AGN jets, and so on. Ruoyu got his PhD from the University of Heidelberg, during which time he was a fellow of the International Max Planck Institute Research School for Astronomy and Cosmic Physics. And then since then, he did several postdoctoral fellowships, including he was a researcher at MPIK, as well as at DAISY. And currently he's at Nanjing. So let's get started. Let's welcome Ruoyu. And as a reminder, we are recording this for our YouTube channel. Feel free to put your questions on chat. And the first part of the talk will be about 50 minutes, and then we'll have questions related to the talk, and then hopefully a nice discussion in the last 30 minutes. So thank you all. And Ruoyu, you want to share your slides and screen, and let's get started.
Yeah. Thank you for the introduction.
Yeah, you're on full screen. Yeah, perfect. Thank you.
Yeah. Okay. First of all, I want to thank Rashmi, Felix, Paulo, and Yuri for the invitation. It's my great pleasure to talk about the gamma ray pulsar halos here. This talk is mainly based on one of my paper published recently, which can be found via this archive link. I would also recommend audience to read two other review papers on this topic. They have different focuses from mine. Okay, so this is the outline of my talk. Okay, this is the outline of my talk. So first, I will briefly introduce the current observations on pulsar halos and discuss the theoretical models. Then I would discuss the physical implication from pulsar halos, and also give a personal opinion, probably biased opinion on how do we for the future study on this object. So pulsar halos obviously are related to pulsars. And the pulsars are highly magnetized and fast rotating neutron star. Okay, neutron stars. So if we assume its surface magnetic field as a magnetic dipole, then we can write the electromagnetic luminosity radiated by the pulsar when it rotates in this form. This P is the magnetic field, and R is the radius, and P is the period. And generally, we can, as pulsar radiates electronic magnetic waves, it will also be slowed down. And we generally can write the spin down rates in this form with this n being the breaking index. When n is equal to 3. It is the case of this dipole magnetic field. With this assumption, then we can derive the spin down luminosity involved with time in this form. So we can see when at the early time, when the t is smaller than tau means the initial spin down time scale, the spin down luminosity is high and keeps almost constant with respect to time. And after T nur, the spin down luminosity drops quickly with time. On the other hand, the electron and the positrons in the magnetosphere of pulsars will be carried away by this electromagnetic wave in form, which is in the form of pointing outflow. At some radius somewhere, which is suggested to be 30 to 50 times the light diameter of the pulsar, then the magnetic energy of the will be dissipated and converted to the kinetic energy of these electrons and positons. So the pulsar, so this pulsar wind will be accelerated to ultra-relativistic. The bulk Lorentz factor can reach 1,000 to 1 million or even higher. And then when this ultra-relativistic pulsar wind encounters the ambient medium, such as the supernova, the ejector of the supernova explosion, then it will generate a strong termination shock, and this electron and positrons will be further accelerated at the termination shock. So when the pulsar wind expands into the supernova ejector, the reverse shock can also propagate back to the center, and at some time later, they will collide with each other. So this figure shows the multi-wavelength observation of the very famous Crab nebula, and from the detection of the spectrum, we know this nebula are guaranteed high energy electron and positron accelerators, especially from the measurement of LASO at the PeV energy, and also as well as this GeV detection of the this synchrotron tail, the tail of this in the spectrum. We can know the maximum electron energy in the Crab nebula can reach PeV energy. As I mentioned, so at some time, usually it's around like 10 kilo years after the supernova explosion, the reverse shock of the supernova remnant will collide with the pulsar nebula. During the interaction, some properties of the pulsar nebula, such as the size and the magnetic field, can change dramatically. And importantly, also the pulsar nebula can be disrupted or partially disrupted during the interaction through the this Rayleigh-Taylor instability, for example. Then the accelerated particles inside the pulsar nebula can escape to the ambient medium. So this figure shows the measurement of the this pulsar nebula of Vela, and the left panel is the extended radio nebula, which is considered to be produced by this escapes pairs from the pulsar nebula, and the right panel shows the center region, the Hess measurement, and the center region. This are considered to be powered by this newly injected, newly accelerated particles. So. Most pulsars have a proper-motion velocity, which they receive at their birth due to the little kick. The general proper-motion velocity is about several hundred kilometers per second. So after some time, the pulsar due to this proper-motion, the pulsar will cross the boundary, the front of the supernova remnant, because the supernova remnant will be decelerated due to the when they're expanding. So this cross usually happens at several tens of kilo years, but it also depends on the ambient medium and the proper-motion velocity. After that, the pulsar will goes into the interstellar medium, and the proper-motion velocity is generally larger than the sound speed in the ISM, so it will drive a ball shock, and the ball shock will and makes this pulsar nebula as this comet shape. Usually, this is a sign for like middle-aged pulsar when they propagate to the ISM. So this figure from Greener's paper, they summarize the three evolutionary stage of pulsar nebula. So in all three stages, we have detected corresponding astrophysical counterparts. So pulsar halos are usually considered to occur at the third stage when pulsar has already leave the parent SNR. And sometimes it can also occur at the second stage. So because at this stage, some particles can already diffuse to the ICM and leave the pulsar nebula. So in this ICM, in the interstellar medium, this escaped electrons or positons, they can upscatter the photon from CMB or this background infrared radiation and upscatter to TeV energies and produce this very extended halo-like sources. So this picture is actually consistent with an earlier prediction by Felix. He studied this the diffusion of this escaping particles, escaping electrons or positons from the this leptonic cosmic sources. Okay, so for the first pulsar halos are detected by Hawk around the pulsar, around the Geminga pulsar and this Modron pulsar. Obviously, this we can see the extended emission detected by Hawk here cannot be explained as their pulsar nebula because in X-ray band we see the pulsar nebula is quite small, quite compact with only 0.2, 0.3 per second. But size of this extended source around this to middle-aged pulsars have like at least 20 or to 30 per second in radius. A very interesting feature is the surface brightness profile in TeV band. We see here is a quite steep decline with the increasing radius from the pulsar's location. So this based on this steep intensity profile, people derived that the diffusion coefficient is quite small here. It's at 100 TeV, it's about 4.5 times 10 to 27 centimeters square per second, which is 2 or 3 orders of magnitude smaller than the standard diffusion coefficient in ICM, which is derived from this primary to secondary cosmic ray ratio. Okay, so another pulsar halo is detected by LASSO later. So this is around another middle-aged pulsar, J0622 plus 3749. And we also see this kind of a steep decline of this intensity profile in TeV band. And the derived diffusion coefficient is also quite small and consistent with what derived for this Geminga pulsar and the Modron pulsar by Hawk. So here we compare the intensity profile of the 3 pulsar halos, and also we see the properties of the pulsars have similar properties. For example, they have similar rotation period, similar age, which are all beyond 100 kilo years, and the spin-on velocity are around a few times 10 to 34 seconds. So I mean, in principle, there should be more pulsar halos around this middle-aged pulsar, but there are many of them in our galaxy. And this figure shows the recent discovery by Hawk around this middle-aged pulsar, this J0359 and the J0358, which also has age around 100 kilo years. And another example would be this the Hess source, this J1809 minus 193. We can see here the extended emission around this energetic pulsar. So this pulsar is a bit younger than this Geminga pulsar or Modron pulsar is only have 50 kilo years, but it could be at this second stage and in the transition from a pulsar nebula to a pulsar halo. So the multi-wavelength observation on this pulsar halo are also important. So at the GeV band, the Fermi-Net can, in principle, can measure this diffusion coefficient independently at a lower energy, and this can serve as the test for this slow diffusion require the slow diffusion zone. And in X-ray band, if we assume a typical magnetic field of 3 microgauss for the interstellar medium, then we'll see this X-ray emission are produced by the same population of electrons that produce the TeV halo. So X-ray observation can also provide an independent evidence for this slow diffusion for their to study the transport of these pairs around in the Pulsar halo. So, but search for GeV Pulsar halo, I mean, mainly result in non-detection. So this is a search in GeV Pulsar halo around Jaminga by our group. We perform a study and analyze in ROI of 40 degree times 40 degree, and we only give some we only obtain some upper limits for this halo at the GeV band. So this gives some constraint on the injection spectral index. But this study is not I mean in another group by tomorrow at all. They found actually they claim detection of the Pulsar halo. This is because they use much larger ROI, like let's say 70 degree times 70 degree. Basically, we recently try to reproduce their results with using also a very large ROI, and we generally we can reproduce their results. But to me, I think one uncertainty is that given such a large region, actually the obtained result could be subject to some systematic uncertainty. For example, due to the diffuse background. So I think this we need further study on this region for this GeV halo around Jaminga. And the search for GeV halo around other Pulsar halo candidates are all result in no non-detection. So it could mean that the injection spectrum is hard. The search for X-ray halo also result in new results. So here are figures for this Chandra's observation and the XM Newton's observation on the Jaminga. Because they limited the field of view, the Chandra and the XM Newton's observation only cover the very center region of the halo. So in this observation, if there fully exists X-ray Pulsar halo, I mean almost the entire the field of view are filled with this X-ray emission of the halo. So it is difficult to distinguish the halo's emission from the background's emission. So in this case, for a conservative estimation of the flux, we only subtract the background. We only subtract the instrumental background and leave and also there's some apparent point sources in the field of view, and we leave all a cosmic background there. And from this, we make this count profile, one-dimensional count profile with the 0 at the Pulsar's location, and then we can see, except in the very center region, which is dominated by the PSF of the emission from the Pulsar nebula, at the larger radius, the count profile is flat. So this means the X-ray emission in this region is dominated by the background. And based on this measurement, then we can put some upper limits of the X-ray halo's emission as this a few times 10 to minus 15 ergs per centimeter square per second. So in this case, if we when we try to reproduce the TeV profile measured by Hawk for the entire halo, we should also make sure the X-ray emission, the X-ray flux for this very center region does not exceed this upper limit. So this gives a strong constraint on the magnetic field in the Pulsar halo. So this figure in the left, when we assume 3 microgauss magnetic field, we can see the TeV intensity profile can be reproduced and the spectrum can be reproduced, but the simultaneously produced X-ray flux greatly exceeds this measured upper limit by 1 order of magnitude. So to make this X-ray emission, expected X-ray emission consistent with this upper limit, we have to lower the magnitude up down to 0.8 microgauss or even lower. So this is significantly smaller than the typical interstellar magnetic field. Another possibility would be introduce a hadronic arranging for the gamma emission. But in this case, we found the required energy budget for cosmic ray protons are too large. So this cannot be the case. So with these observations, then we can look into the theoretical models. So for model 1, we is referred to this isotropic diffusion model with a suppressed diffusion coefficient, which is also the most commonly considered model currently. So in this model, usually people assume suppressed diffusion zone for inner halo, usually within like 30 parsecond or 50 parsecond, and outside this radius, the diffusion coefficient becomes the standard diffusion coefficient in the ICM. And in this case, the particle density would be proportional to this 1 over r at a small radius. The key issue for this model is to generate a slow diffusion zone. And one plausible mechanism is this cosmic ray self-regulation via this streaming stability. So in this case, when cosmic ray have some gradients in their density, then they will have a net cosmic flux. Then when cosmic ray interact with scattered with the alpha wave, then this cosmic ray will astropize in the wave frame. So it means the wave also gain some momentum from the cosmic rays because the cosmic have this net momentum with mvd. So by doing this, the wave also gain energy, gain momentum, and their amplitude is amplified, so that they can slower down the diffusion speed of the cosmic rays. So usually people do this calculation in a one-dimensional scenario. They consider cosmic ray are injected into a magnetic flux tube in this cylinder, and they when they propagate in this cylinder, then they gradually amplify the difference, and the diffusion coefficient becomes lower and lower. This is a recent study by these authors. And they find below, let's see here, below 10 TeV, the diffusion coefficient is significantly suppressed. It's suppressed down to like 2 or 3 orders magnitude compared to the standard ICM diffusion coefficient. However, above 10 TeV, actually this suppression becomes weaker and weaker. We can see at this 100 TeV, the diffusion coefficient is almost similar to that in the standard ICM diffusion coefficient. So this is because this mainly has 2 reasons. So one is because the amounts of the injected pairs at this high energy is quite small, and the second is because the cooling time of this very energetic particles is very quick. So only very recently injected pairs can survive at today. So this will makes the growth rate of the turbulence quite slow. So if one consider a 3D case, then the volume that cosmic ray distribute becomes much larger, and it dilutes the cosmic ray density. So it will further make the this instability less important at this high energy. So this is consistent with an earlier study by this Fang et al. In 2019, and in this paper the authors consider the most optimistic case, which means they do not consider the wave damping, and they do not consider the cooling of injected electrons and positrons. By doing this, they find the streaming stability can at most reduce the diffusion coefficient down to like 10% of the standard diffusion coefficient in ISM, which is not sufficient to explain the observation of Hawk. But they also in the same paper they consider that the superlunar remnant of this Jamaica pulsar can generate some turbulence. So in principle, I mean, as long as the magnetic field inside the superlunar remnant is low, then it is sufficient to make this to amplify the turbulence to the required level. So this is maybe the possible solution for such a slow diffusion coefficient. But if the pulsar has already left the superlunar remnant, then we need to find another origin for this slow diffusion coefficient. Okay, then about the second model, the author considers this ballistic propagation of these particles within one mean-free path, because when particles are just injected, they have not been deflected significantly by the turbulence. So basically, you can consider this particle they will propagate more like in a ballistic way instead of a diffusive way. Therefore, in this small radius, when r smaller than the mean-free path lambda, the particle distribution will be like this Q1 over r to the minus 2, r to the minus 2. This distribution is much steeper than previously than expected in the previous model. On the other hand, because since particles are at small radius, they only move in radial direction, so their emission will also concentrate in this radial direction due to this relativistic beaming effect. So one observer, if the observers look at this the pulsar's direction, they will receive the emission of the electrons or positrons here. But if they look at other direction, for example, if they look at this direction, they will not receive the irradiation because the particles here propagate in this way and they radiate in this way. So considering this, in fact, they don't need the authors find they don't need introduce a very small diffusion coefficient to reproduce this steep profile. In previous model, the reason for a slow diffusion coefficient is because we want to cool the particles before they diffuse to large radius, so that these particles can have a very steep profile due to the cooling effect. But in this model, when they consider this ballistic propagation, actually they don't need to cool particle, because due to this much steeper distribution, also due to this this beaming effect, they obtained surface running profile are already steep enough to reproduce this observed profile here. But one potential problem for this model is the energy needed for pairs, because in this case the diffusion coefficient is large, so particles basically distributed in a much larger volume than that's in the previous model. It means if you inject the same amount of pairs, the density will be diluted and the intensity will be diluted. So to compensate this, you need to inject more particles into the ICM. Then they also found that there's an eta factor, which means the fraction that the energy converting from the spin down luminosity to pairs luminosity need to be around unity or even larger than unity for some cases. So this is the potential problem for this model. And another potential model is that actually at the small scale, particles do not really move ballistically, because although the mean free path could be large, but the normal radius of particles can still be quite small. For a typical interstellar magnetic field, the normal radius of 100 TeV particles is only about 0.01 to 0.1 per second. So particles would rather they will move in a helical way, I mean along with the field line, instead of propagate in a straight line. So in this case, the angular distribution of the particles, they will be much broader than previously considered. Only consider this the beaming effect. So what will be the resulting intensity profile? I think need a further study, considering this elliptical motion of particles. And the third model I would like to introduce is this isotropic diffusion model. Because in the interstellar medium, it's not always super harmonic. Actually, somewhere in the SM could be subharmonic. It means the turbulent component is smaller than the regular component of the magnetic field. So then, in this way, in this case, there will exist a mean direction of magnetic field in certain region within one coherent length, which is really like 2 to 100 parseconds. So in this case, particle will, I mean, their diffusion no longer holds an isotropic. In this case, a particle diffuse more quickly parallel to the magnetic field than they diffuse perpendicular to the mean magnetic field direction. So particle distribution will not be a sphere, but rather like resemble a cylinder. So with this z-axis, the mean direction, the mean direction of the magnetic field. So the pulsar can be the whole entire distribution could be still with symmetric with respect to the pulsar. But then the projected morphology of the pulsar halo would then depend on the in which angle we view this halo. So this angle phi here means the angle between the line of sight of observer to the pulsar and the direction of the mean magnetic field in this region. So if this phi, this viewing angle, is very small, then we will view the halo in this way. We will see, then we will basically see more or less spherical-like halo in the sky. And the size of the halo would be dominated by this perpendicular diffusion coefficient, which is much smaller than the parallel diffusion coefficient. In this case, the low X-ray flux can also be explained because when we have a very small viewing angle, then the particle they will radiate to us also has a small angle, has a small pitch angle with respect to the magnetic field line. Where we know that the synchrotron power highly depends on this angle between the particles, this velocity direction and the magnetic field direction. So in this case, the synchrotron radiation of the particle can be suppressed. So this figure shows the fitting of this model to the spectrum and to the profile. And we find if as long as this viewing angle is smaller than 5 degrees, they basically this model can reproduce the observation. This model also has a potential problem because we do not expect all the the magnetic fields, the mean magnetic field direction in all pulsar halos to be aligned with our line of sight. If we view the pulsar have a larger viewing angle, then we should expect to see an elongated, elliptical halo on the sky instead of this spherical like halo. But this elongated halo has not been observed yet, so this poses a problem to this model, and which we will come back to this point later. So here we have summarized to 3 models. So in model 1, we see the main difference is the diffusion coefficient. It requires a strong suppression of the diffusion coefficient with respect to the standard ISM diffusion coefficient. It means a strong amplification of the turbulence inside the pulsar halo. The model 2, the main difference is the energy budget. It requires almost all the spin-on luminosity convert to the pairs luminosity, where for other 2 models, it basically only requires like 1% or to 10% of spin-on luminosity convert to pair luminosity, depending on the injection encryption spectrum index. For model 3, the isotropic model, the main difference is the topology of the magnetic field, also the strength of the magnetic field. Here, the magnetic field, we don't need to invoke a very small magnetic field, but we need there exists a strong, important regular component of the magnetic field inside the halo. And we also need a specific orientation of the magnetic field so that we can reproduce the observed morphology. Okay, so regarding the implications, so although these three models they have different expectation of the pulsar halos some properties, but one common factor is that the pulsar halos inject a lot of energetic particles into the ICM. So for very high energy, let's say for high energy electrons above, let's say above 10 TeV, the cooling time in typical magnetic field of ICM is quite short. So the diffusion length, which is defined as the typical diffusion distance before the particle cools, or within the edge of the pulsar halos, it's quite small. Even with the standard diffusion coefficient shown as this red curves here, the diffusion length for electrons above 10 TeV or 100 TeV, you see it's only like 700, 600 per second or 700 per second. So it means that most injected electrons at this high energy will deposit their energies in the galactic plane. Considering this fact, Lindner and Bachmann they suggest that if every middle-aged pulsars host a pulsar halo, then the superposition of their emission could contribute significantly to this diffusive galactic background, which can even exceed this diffuse emission produced by cosmic ray protons interacting with the ICM above a few TeV. So in this case, we may expect that the pulsar halos could constitute a very strong background for when we search for other TeV sources, especially this extended TeV source. So if we want to get accurate properties of this other extended TeV source, we need to accurately subtract the influence, the contamination from this the superposition of this pulsar halos contribution. And also recently, another group they proposed that the collective emission of pulsar halos in galactic plane can even have very significant contribution at the sub-TeV band in this diffuse galactic emission. Okay. Another important implication is the origin of the positron excess from pulsar halos, because pulsars have long been considered as the origin of this positron excess, which at 100 to above a few tens of TeV to sub-TeV energies. And the pulsar halos actually they make us able to see how these positrons they escape from the pulsars, and we can know how much of them escape the pulsars. So there are many of studies here, and okay, due to the time, I won't discuss them in detail. And another important implication of pulsar halos is that it can shed some light on the properties of the interstellar turbulence. From the size and their morphologies, we can extract the diffusion coefficient, and which also means the turbulent level in the interstellar medium. And this can give us some hint on the global transport of cosmic ray in the galaxy, and also the origin of cosmic rays. Okay, so then how should we figure out the nature of pulsar halos? I think the most important thing is the observation. So currently, actually, the detected pulsar halos is the number is quite few. If we assume every middle-aged pulsar halo, every middle-aged pulsar can host a pulsar halo, then we should expect, let's say, at least 10,000 pulsar halos in our galaxy. But currently, we only detect only a few of them, and I mean, including some candidates. So the first thing is that we need to discover more pulsar halos, and then we also need to have an accurate measurement of their spectrum and their morphology, so that we can extract these important physical quantities from the observations. So here, I think this the new generation of gamma ray instrument like LASSO and CTA and SWOGO can play an important role here. Also, we should not forget about this the extra instrument of large field of view, such as the Rosetta. And here, this Einstein probe is also have the large field X-ray instrument, which will be launched this year by China. So with these observations, we can, we can do some further studies. So first, I think LASSO and SWOGO will play a key role in detection pulsar halos. This first because they have a larger field of view and they are very suitable to detect these very extended sources like pulsar halo. And they also have a high sensitivity, above 10 TeV, where since they like the spectrum of pulsar halos peaks. Also, above 10 TeV, the physics is relatively clean because the streaming stability here is unimportant. Also, the cooling time of this very energetic electrons is quite short. So it's the halo, the morphology, the size of the halo and the morphology of halo is irrelevant with the early evolution. For example, here we show the simulation of the pulsar halo produced at the 10 GeV band and also 10 TeV band, because the 10 GeV band, the emitting electrons have very long lifetime. So we can see at early time the halo, the injected particles are still alive today, and makes this morphology of the halo quite complex. And but for 10 TeV, due to the fast cooling, this halo they always trace the location of the pulsar when it moves. When it moves, so it only have a compact, relatively compact source around this halo. So it makes the detection and also the analyze relatively simple. And also at a lower energy, one problem is that the early injection, because at the early time the spin-out luminosity is quite high. So, but the initial rotation period is not known. So we can see here, if we assume different initial rotation period, actually the resulting spectrum at below TeV, it can be quite different, have a large difference. But we don't know it depends on the electromagnetic environment at a very early time, and which have a large uncertainty. But at high energies, you can see is the resulted spectrum almost independent with this the initial rotation period. So based on this observation, we can try to distinguish different models. For example, for this anisotropic model, diffusion model, because the morphology can show we expect a lot of this elongated halo in the sky. However, due to when we view this halo with a large viewing angle, when it becomes elongated, actually it becomes more difficult to detect them because they are more diffuse. They are like mixed with the diffuse background. So in this figure, we show the expected significance for a pulsar halo above 25 TeV, but for different viewing angle. So we can see when the viewing angle is 0, it means we in this case the expected detection significance is quite high. But if we view the angle at 30 degree, 60 degree, or even 90 degree, then the expected significance drops significantly. However, for like the sensitive this gamma ray instrument like LASSO, it should be able to detect this elongated halo with long exposure, with beyond, if we have a few more years exposure, we should expect to see some elongated halo. So this can serve as a critical test for this model. If we do not detect any elongated halo, it means we can rule out this model. For this the model 2 with this ballistic propagation, the main difference is it can inject much more particles than other two models. So this will reflect in the diffuse gamma ray background. So in this figure, we show the measurement of this diffuse gamma ray background in galactic plane by Milagro and AS gamma. We can also calculate the expected emission from pulsar halos from all this middle-aged pulsars now recorded in this 18F log. Then we can use this upper limit, this measured flux as an upper limit to constrain the amount of this pairs injected in this pulsar halos. So based on this current observation, we can basically, you can see for a conservative constraint, we can limit this conversion efficiency below like 0.2 or 0.3. But of course it also depends on the some other parameters like the maximum the cutoff energy in the spectrum or the injection spectrum index. So if LASSO and this SWOGO can have a more accurate measurement for this diffusive gravity emission, then we can have a lower upper limit here, and then it means we can give a stronger constraint. So this could be used to rule out this model 2, which with this ballistic propagation. And X-ray observation would be also very useful. So here we show the expected X-ray flux for some pulsar halo and pulsar halo candidates. And this dashed this magenta line here shows the Eurosita sensitivity for different exposure time. Basically, we think with reasonable exposure time, the Eurosita should be able to detect this the corresponding X-ray halo. And also because X-ray instruments have a much better angular resolution than gamma ray instruments, so they can have an accurate measurement for the intensity profile. Here we show the expected X-ray intensity profile of 3 models. So this solid curve means the isotropic model with a suppressed diffusion coefficient, and this dashed curve means the model considering the transition from ballistic propagation to diffusive propagation, which you can see shows a different different shape of this profile, because this is how to say it goes in this way, but this I mean the tendency of this curve is opposite from this isotropic diffusion model. While for this anisotropic model, so if it depends on the profile depending on the viewing angle. So if we view it with a small angle, then first the intensity is quite low. It probably cannot be detected, and also even it is detected, it shows a quite more extended behavior of this curve, of this intensity profile. Okay, I think I used up the time, so here's my summary. So first, pulsar halos are new class of TV gamma ray sources. It's usually with the extension of several tens per second. And the gamma ray emission of pulsar halos are produced via the inverse competent scattering of this escaped electron-positron pairs of CMB and also infrared backgrounds in the galaxy. And pulsar halos are currently have not been detected significantly at the GeV and the X-ray band. But these multi-wavelength observations are very useful to understand its nature. And currently, I think there are main 3 models, and all of them have pros and cons. For model 1, the best thing is that it's very simple, and we can also reproduce most observed feature of Pulsar halos with this model. But we need to, in this model, we need to explain the origin of the slow diffusion and also the origin of the small magnetic field. For model 2, the good thing is that it don't need to invoke a very slow diffusion region, but it could suffer this energy crisis, and also this ballistic propagation is kind of unphysical. So the particle should be moved in a helical way, and how it influences the result need to be further studied. And model 3. Consider also don't need to invoke small diffusion coefficient, and also the magnetic fields and the magnetic field strength can also be the typical value. But it may predict too many elongated value halos which have not been detected, and this can be checked by LASSO in a few years. And the Pulsar halo have important contributions to many aspects of high energy astrophysics, such as the positron access and the diffuse scattering background. So if we can understand the properties of Pulsar halos better, we can also have a better understanding of this important issue in high energy astrophysics. And with this new generation gamma ray instruments and extreme instruments, we are I believe we can unravel these puzzles of Pulsar halos. Okay, that's all. Thank you very much.
Yeah. Great.
Hello.
Thank you very much. Yeah, Felix, you wanna? Yeah, thanks for that great talk.
Yeah, thank you, Paulo. But I cannot now continue because I'm sitting in the seminar, the conference hall, so there are people are leaving. So maybe you could just run this. But I like to just only ask question, and then I'll leave. Ruoyu, what about this? Yes, I think you are right about this ballistic, but ballistic also, as you mentioned, is one of our squares, so that is an additional advantage. I think this slow diffusion is kind of very strange thing, especially if you ask in both sides, you ask very small magnetic field and very slow diffusion. So, I mean, you should run at the level of bomb diffusion, maybe with such a small magnetic field. So it's because magnetic field also reduces theoretically, even bomb diffusion could be. So the another issue is what about the advection instead of diffusion? Because then also you'll have R square.
Yeah. Yes. Exactly.
And then no one discuss. To my surprise, no one discusses most natural thing. Well, including me.
Yeah, I agree. I mean, considering advection could also make make this steep decline of this surface profile without invoking slow diffusion. But the thing is that what advect these pairs in ISM, this would dramatically change the physical picture for some evidence.
Yeah, but in this advection, I mean, for Geminga, in fact. It is small. It's not 10 parsecs, so it still is. I know Geminga is a very special source. Actually, I don't like Geminga because for that reason is very specific one. But advection is another way in general, not just for Geminga. I mean, another way to get this tip. And just my last comment is just all results are based on the 1 or 2 first points. I think that is a bit better. I mean, the profile. It is, and then you change a bit profile, then you get something else, right? So, and that is a point. And second point is, it depends where you take the reference point. I mean, the starting point. If you shift also, it could be this radial distribution could be changed. Now, of course, it's natural to take a pulsar as a starting point. But if some acceleration happens, I mean, hypothetically, some sufficiently far, let's say few parsecs far from the pulsar, then you could have quite different profile. So that also should be taken into account, I think. probably.
Yeah. Actually, I think there is a suggestion that the magnetic reconduction in the tail of the spall shock can accelerate some particles. Yeah.
That was
I
also
think this is possible. This is possible.
And Andrei Bykov had a model.
Yeah. Yes. Bykov.
Yeah. Okay, sorry, I have to leave.
Okay, thanks, Felix.
Bye.
Bye.
Okay, thanks, Felix. Are there any questions? Let's see, or you can. I don't. Okay, I see one by Lars. Okay, go ahead and ask your question.
Yeah. So thanks for the great talk. This is mostly a remark about this system CDHY-1809, which you mentioned, which may be a system which is in a transition between a pulsar nebula and a halo. And for that one, interestingly, we actually see if it is a halo, that it appears elongated a bit.
In this direction.
So in the context of this model 3 that you introduced, where you expect something elongated, that could be interesting. I mean, there could be other reasons for this elongated shape, of course, but I just wanted to make that comment.
Okay. Thanks. Yeah, thanks for the comment. Yes, probably we can try with the model 3 with this force. Yeah.
Okay. Great, thanks. Evgeny, you got a question?
Thank you for your talk. And the question is very simple. If you try to compare the numbers, take the halo and take the magnetic field, let's say just typical ISM magnetic field, and the energy density of it. And then take the energy density of electrons and positrons that are diffusing away from the pulsar, where the energy densities are comparable, at what distance from the pulsar approximately, just to get an idea.
Sorry, comparable with what? Sorry, I missed some of them.
The energy density in electrons, or maybe positrons, which are emitting gamma rays in the halo, and the energy density of the local magnetic field. Let's take ISM magnetic field.
Okay. Oh, let me. Wow, I didn't check this. But probably we can see from some studies here. For example, they calculate this how to say this this is the lower energy. I need to check. So sorry, I cannot answer you here. Where the density?
Well, the background of this question is rather simple. I might be wrong, but it seems that if I just try to estimate by an order of magnitude, then there could be much more energy in the particles than in the magnetic field, if you assume the magnetic field is just not very high. I mean, 1 microgauss or something like this. And if this is correct, I'm not sure that I did the correct estimate right now. If this is correct, then could it be possible that the pairs, the electrons and positrons, are actually affecting the magnetic field in terms of they change the geometry of the field lines, etc. This could be something that makes the surrounding medium very different from typical ISM.
Okay. Okay, we can do a quick check if you can wait me 1 minute. I can quickly calculate that. Just a moment. For example, we assume the injection luminosity to be okay. Okay, we can assume injection luminosity to be 10 to 34. We divide by 4 pi and divide by the diffusion coefficient at let's assume -2 spectrum at then this at 10 to 22, and we over R equal to the this will be the energy density times sorry, at 100 eV. What is this? Okay, then okay, there should be 2 or 3 per second at this radius. It will be become 1 EV per cubic centimeter, right?
Mm-hmm. And this is comparable to the magnetic field, even larger.
Yes, but at a larger radius, I think it's then it will drops the density will drops quickly. Yeah, sure. Okay, thank you. But sorry, I just have one question. So in this, do you suggest that I mean I think it's similar to this self-regulated scenario, right? When it's also the turbulence is amplified by cosmic rays.
In a sense, yes. If you think that the pairs can create the magnetic field of their own, then yes. But sometime in your talk, you said that the streaming stability above 10 TeV could be unimportant, and I thought that even in absence of instabilities, if there is no increment of the magnetic field, you don't want the magnetic field to be large. Actually, you want to make it lower than ISM, not larger. Then you can still change the geometry of the field lines. This is actually what makes the diffusion coefficient much larger than the bond diffusion. This is the geometry of the field lines, and you can change the geometry if there is enough pressure in the particles without incrementing the magnetic field.
Okay.
Yes, but in a sense, yes, it's similar. I agree. Mm-hmm.
Yeah, would that go in the wrong way though? Make the coefficient too large, and then like if the particles sweep everything out, they'll go radially in the limit of zero magnetic field if their energy is much too large. Question again, Ian. Yeah. Either both of you guys are just listening.
Mm-hmm.
Yeah, I mean, in MHD turbulence simulations, I guess if the magnetic field strength is too strong, it stops the particle turbulence and the cascade stops.
Yeah.
So the inverse could happen, but yeah. Okay, I'll keep quiet now. Rashmi, you've been waiting for a question, so are you there?
Yeah, I had a question on that Fermi analysis that you showed. I think it was an SED where you were doing two.
Yes.
Not this one. Yeah, this is the one. So what was the difference between the two? This is the same source that you have, and the upper limits that you calculated for Fermi. This was for an extended source calculation. But what the spectrum looks different for the two, the upper limits. What was the difference in the analysis?
It's basically the important region of interest. The size is different. So for this study is 70 times 70 degree. So in this study it's 40 times 40.
How do you choose that a priori, the size? Is it motivated by something, or how do you decide what region of interest to choose? I mean, it depends. So the Hawk, I can see that the Hawk measurements are the same. I mean, if you look at the USCDs, but the Fermi makes a big difference, right, in the modeling?
Yeah, because I mean, particles emitting at the Fermi band has lower energy and have longer cooling time scale. So, I mean, it is supposed to diffuse to a much larger radius. So we have our calculation is that it can extend the diffusion of this Fermi band emitting electron can extend to like 20 degrees from the how to say, sorry, at least the 10 degree from the pulsar. So in diameter, then it's 20 degree. Then we decide to choose 2 times of this the expected size. It's 40 times 40.
Okay.
This is how we choose this region of interest for this study.
Okay, thank you.
You're welcome.
Yeah. Any questions? So that brings up, what do you assume for the diffuse gamma ray background? Like, did you use Galprop? Because I guess there's a, like Felix showed, there's a uniform density of cosmic rays. If they're molecular cloud enhancements, you can get hotspots with nothing there. So the diffuse background model's super important, and they're unidentified sources and things like that. So what did you assume there, and how sensitive is it? Yeah.
We try basically we try with this the standard the diffuse gamma ray background file provided by Fermi-Net team.
Okay.
And we also try to to relax some the normalization and the spectrum of some background source in this like for FGR list. But it's I mean it does not make much difference. But we can reproduce their result. I mean if we enlarge our ROI to 70 degree. So basically, then you can find a quite in a quite large region. There are some you can find a significance of a Gaussian like structure there, and you can. Yeah.
Wow. Okay. Yeah, because it's a very large area on the sky.
Yeah. Yes. So this is why I keep skeptical on the results. I mean, it could be true, but it's so large and it can contain a lot of influencing factors there.
Yeah. I would say. Okay. And do you have any thoughts? So people have looked at the galactic center, and there's positron annihilation lines, and they said it's from a population of pulsars, some people say, and they claim they resolved some of that background. Do you have any thoughts of that? Is that a pulsar gamma ray halo? You have many pulsars maybe near the galactic center and throwing stuff out. People often say it's dark matter too, but
yeah. But for pulsar halos, well, I mean, at least in the conventional model, we would consider all the accelerated particles are ultra relativistic, so they have very high energy.
Yeah.
I'm not sure they can, because then the cross section can be much smaller than that low energy ones, right?
Yeah.
I have not calculated the density there, but generally, also if they analyze with like position with electron, they analyze there because they have very high energies, so you would not expect the line would be at
right.
at this 511 keV.
Right, but I guess it's the same source or not, or because people said pulsars are responsible for the positrons, which then cool down or something before they annihilate. But and maybe that's impossible. But I guess so. People always talk about the astrophysical background for dark matter models, and I guess this is one of the main ones. Even though you're right that these are ultra relativistic particles, but it's all connected. I wonder. Yeah, in the galactic center, there's in principle a much higher magnetic field, like a milligauss. There's a torus. Would that change things and trap stuff?
Okay.
Has anybody done some modeling of that, I guess, or does anybody know?
But I think yeah, I think you have a point that if they have a strong magnetic fields, then they can trap and they can cool these relativistic particles quickly. Maybe makes them easier to be captured
on there.
Yeah.
Okay. All right. Any other questions? If not, I can ask a few more things. But anybody else? Or if not, I guess I remember Andrei Bykov's talk. And so some of the conditions for acceleration at the interface of the pulsar wind nebula or gamma ray halo might exist. So how do you rule out, we talked about sort of extended acceleration or reacceleration or something, since you have an outflow converging on ISM, and you have cosmic rays maybe running ahead and generating turbulence, so then you could have Fermi 2 picking up, maybe not to ultra relativistic energies, but how do you know you don't have a reacceleration or in situ acceleration is responsible for part of the halo emission?
Okay, so yeah, that's a good question. Actually, I think this is similar to what Felix suggested.
Yeah, exactly. Yeah.
So if we have another injection center, or this picture could change. But I think another thing that we need to search in other wavelengths, right? It is true that actually for example, you can see on for this Hawks observation around Jaminga. Actually, the source center here is not very consistent with Jaminga's location. It has some small offsets from the Pulsar's location. But if let's say if you see here is another source center here, we have a reacceleration. Probably it will also read it in other wavelengths. So probably in X-ray, I mean, we are synchrotron emission in X-ray or in radio. I mean, we don't have these observations yet. I think we need more to study this scenario. I think we cannot rule out this possibility. It's possible.
Okay.
But,
yeah. Wow. Because I think in general, it's a very big challenge for most analyses to work on such large area on the sky.
Yeah.
Have you, do you know, I guess the Rosette observations were good enough to pick up some of the Fermi bubble?
No, Rosette too shallow. It's
too shallow for sure. Okay. Yeah. All right. And yeah. Any other so another question I had is to the extent that you have observed the synchrotron tail, which wasn't totally obvious, is it consistent with the gamma ray TV tail? Because if there was like you said, anisotropic field or something, you can change the synchrotron emission and you would have a mismatch between the gamma rays and the synchrotron. Is that an issue, or are they perfectly consistent, or we just have not detected enough of the synchrotron emission to say that's another test of like anisotropy and things like that?
Right. Yeah, I think the situation that we don't have a sufficient observation to just on that. Yeah. I mean, currently, but because Pulsar halo, I mean, we only have a few cases, a few Pulsar halos detected, and also I think multi-wavelength observation, especially as you said, for this very extended region, it's not easy. Yeah. So I just hope the community can have more interest in this kind of source and do some observations.
Okay. Maybe some observers can say, or does anybody know, has LASSO discovered, I know they have more, are there any surprises, or like with Hawk or even Veritas, have you searched for halos? Is there something new coming, or have we seen all the halos that are there already?
Yes, LASSO have detected some new sources. Some of them are halo candidates. I think in this ICIC this year, there will be talks on that.
Okay.
Currently, I cannot see much.
Yeah. That's great. Any comments from other observers or Veritas or people looking at galactic model? Or I guess not. Okay.
I have to get to another meeting, so I'm just going to jump out here. But Ruoyu, I just want to say thank you for a really excellent talk. That was great.
Thank you. Thank you for the invitation.
Send me your slides for posting on the website.
Yeah. Okay. I'll send you later.
And see everyone in 2 weeks. But I don't want to stop the discussion, which is really great. So please continue.
Yep. So any other questions there? I'm talking too much, so I could have more, but so well, if no one's saying, another question I thought, in these models, besides the acceleration, do you have the particle aging? Is it do you have instantaneous acceleration at the center? Like what's the assumption? And then they just diffuse out. Is that what's going on, or could there be evolution somehow, some extra evolution? Like the magnetic field profile changes, so the diffusion coefficient also changes. So how sophisticated are the models, and do you think, for example, if someone did an MHD simulation, we could do better or constrain things better? Like we can now 3D MHD.
Yes, exactly. I mean, currently the current model basically, I mean, have very phenomenological assumption. Just we inject particles there and let them diffuse in the surrounding medium. I think what you said is very important, especially for this for those low energy particles, because they have. I mean, if you just put them inject them into the ISM. For typical interstellar medium magnetic field, they can survive for a quite long time. But we know I mean, especially at early time, they are injected into the Pulsar nebula, and from let's see, from this, I have a figure here. Yes, this one. From this one, actually, you can see at the early time, the magnetic field change quite quickly, and also here due to the this compression due to the reverse stroke, the magnetic field also has increased again. So I think I mean, these low energy particles, I mean, let's say 100 GeV particles, they can be cooled inside this strong magnetic field. If you consider the first like, let's say a few tens thousand years confinement in Pulsar nebula, it could change the injected spectrum.
Yep.
So I agree with you that more sophisticated, we should consider like this hydrodynamics and also evolution with important properties inside the Pulsar nebula, and also model the escape of the particles, and then diffuse them, inject them into the ISM. Consider the ISM diffusion. I think Pulsar has some work on maybe on this model, this escape of pairs. But in his paper, he does not consider the further the further diffusion of these particles in ISM. So I think currently no one has done such a complete evolution from Pulsar nebula to Pulsar halo.
Yeah. And okay, any questions for myself? Where do you draw the line or the definition between Pulsar wind nebula and Pulsar halo? I mean, what's
yeah, that's difficult. I would say I would say if the pulsar goes into ISM, and then when this particle emits in the ISM, I would call it pulsar halo. But
Yeah.
if it's still how to say, yeah, it emits in this advection, maybe advection dominated Pulsar nebula, or it is still inside the SNR, maybe. I mean, it's not just the difference is not that sharp, but
yeah.
I mean, someone would disagree, but I would only call those quite old at old time when sorry at old age when this pulsar moves to ICM, then such kind of source pulsar halo.
Okay.
And in this case, could be a mix of pulsar nebula and pulsar halo, maybe.
Yeah. Okay. That's great. And then when you said above 10 TeV, things are simpler, but you're still sensitive to the injection spectrum, I guess, the primary injection spectrum. So is it true because of the short lifetime, you don't worry about what happened in the past so much, so it's cleaner that way, but are we not still sensitive to the initial injection spectrum and or details of the magnetic fields? And I guess
at least for this, at least for this typical magnetic field, like let's say 3 microgauss, 5 microgauss, then these particles will cool sufficiently fast. You see here, for example, 10 TeV. No, I mean 10 TeV gamma rays. 10 TeV gamma rays are usually produced by maybe 50, 60 TeV electrons, right? So when this the target photon field is CMB, so this gives you like maybe 30,000 years or 20,000 years cooling time scale. So I mean for pulsar halos, usually the pulsar age is more than 100 kilo years. So this for the late time injection, the pulsar probably the pulsar already left the circular remnant, so the environment becomes more or less clean, more or less simple. So so I would prefer to study this very high energy part.
Yep. Okay. Which is good philosophy. All right, that makes sense. But it would be nice to have a population to compare and see, but we only have 2, right? You said, or to test. Yeah.
Sorry.
No, yeah. So you could imagine different pulsar systems will have different injection spectra, possibly.
Oh yeah.
Not so universal, but is it true we only have a sample of 2 right now, or basically?
Okay, so these 2, I mean, people generally consider they are pulsar halos, and for this LASO, this J0622, I think we can also sure that they are pulsar halos, because in this region there are no other astrophysical candidates. And also no gas here, so it cannot be from hadronic emission. So I think in most of the cases it's also pulsar halos. And there are some candidates, for example, for this newly reported source by Hawk. But here are two pulsars, and both of them are energetic. So here it could be a mixture of both their contribution.
Yep.
And also, for example, this source, it's I mean, the definition is it's not so clear. So we don't know whether we can call it pulsar halo, or probably I mean, this extended emission could have other origin, like hadronic origin, because there are gas in this region.
Okay. Yeah, that's good. Yeah.
So I think we can have we can firmly say pulsar halo are 3, and we have some more, maybe 2 or 3 more candidates, likely candidates, and have other things we cannot identify. that like this.
Okay. Yeah. All right. That's cool. All right. So things have evolved even in the last couple of years. Okay. Yeah, that's very interesting.
Yeah.
All right. So I think we're getting close to 10:30. I've been talking too much. So last chance for questions, I guess. For you. Okay, well, question. Michelle, go ahead.
Yeah, sorry, a very quick one. I was wondering for all those different candidates for Halo, TV halos. So would we expect to always have measured the proper motion of the pulsar in the system and to have values as high as the 400, 500 kilometer per second and so on, in order to firmly identify the system as a evolved pulsar wind nebula that is transitioning or has transitioned into a halo? I was just wondering your opinion on that.
So for, I mean, for from the point of view of a proper motion.
Yes, I mean, well, there have been already quite a few pulsars where proper motion has been measured, and more or less, let's say the average is around 200, 300 kilometers per second. It seems that in order to explain, at least in the ballistic scenario, that you will need to require to understand why the position of the current position of the pulsar with the position of the emissions in gamma rays is so offset and so on, and especially in halos, we are talking about even more involved systems. So I was wondering, in terms of the definition of a halo, or at least for when considering if a candidate source could be a TV halo, does that require to have measured the proper motion of the pulsar that seem to be associated?
Okay. So I think one possibility is that because what we measure is only the projected velocity on the sky, right? So I mean, we don't have to require the pulsar have proper motion, because in some cases I mean, the projected velocity could be small. I mean, most of their they can move in this line of sight direction. In this case, then you cannot measure the proper motion, but it has, but you just cannot you just cannot measure it, because it does not move on the sky, but it moves in the long line of sight. So in this case, I mean, not all the pulsars of I mean, hosting pulsar halo have this significant proper motion. And secondly, pulsar at the TV band, actually, you won't see this a special morphology that induced by the proper motion. Because this because due to the faster cooling of this very high energy electrons or positrons, this halo would always surrounding the pulsar looks like have some spherical feature. But at the GV band, if we can detect something some this like the drop like this morphology, or but it should not be so ideal. So we I mean, in principle, we may we could try to ascribe the special morphology to the proper motion, but at the EV band or even 10 EV band, it's quite difficult to have difficult to see this elongated structure due to produced by proper motion. So if we, I mean, from this point of view, I guess it's not so easy to have a very clear definition of I mean, of pulsar halos from pulsar wind nebula.
Indeed, but at some point, in order to consider the fact that, well, a halo is something that electrons and positrons that are no longer confined within the pulsar with nebula need a reason for the pulsar that is injecting the electrons to be outside the pulsar with nebula system, and as well as in our system. And the initial kick given to the pulsar seems to be one of the main factors to at least explain this type of transition between that.
Yes,
But
yes.
Fair enough. Thank you for your answer.
Thank you. Just one more comment. I think I think it's very good to take them as a hint for pulsar halo, but probably probably not so decisive to identify it as a pulsar halo.
Fair enough. Fair enough. Thank you.
You're welcome.
Yep. Okay, so I think that was very interesting. Okay, I think we should stop because I myself have to leave also. So let's thank Ruoyu once again, and thanks for a great talk. And we'll see you in 2 weeks. Okay.
Thank you very much, and thank you for your questions. Bye.
Okay. Thanks. Bye, everyone.